Hello and welcome to the AI Research Roundup. I am your host, Alex. Today, we're diving into a paper called Gaze-LLE, Gaze Target Estimation via Large-Scale Learned Encoders. The main goal here is Gaze Target Estimation, which is essentially about predicting where a person is looking within a scene. Now, previous approaches were quite complex, needing separate models for the person's head, the background, and more. This paper introduces a much cleaner method. It uses a single powerful vision model, DynoVive2, to create one representation for the whole scene. Then it simply adds a positional prompt, which is a small cue telling the model where the person's head is, and a lightweight decoder does the rest. It's a great example of achieving top results through simplification. And what's really great for the research community is that the authors have made all of this work public. They've released the official code for Gaze-LLE on GitHub, and it's very comprehensive. You'll find their pre-trained models and also the scripts to reproduce their findings on standard datasets, like Gaze-Follow, which is a large collection of images used specifically for this task of tracking where people are looking. They even include a Google Colab demo notebook, which makes it incredibly easy for anyone to try out the model without a complex setup. Alright, and this figure here really visualizes that simplification I was just talking about. At the top, you see the prior approaches. They're quite busy. You have separate inputs for the head, the scene, and even things like depth. Each one gets processed by its own encoder, which is just a part of the network that extracts important features. Then they all have to be fused together. But if you look at the bottom, the Gaze-LLE model is much cleaner. It uses one single frozen scene encoder, meaning it's pre-trained and not modified, and simply injects that small positional prompt I mentioned to a lightweight decoder, which then generates the final gaze map. So this table really drives home why that new Gaze-LLE architecture was so important. The researchers took several existing models and tried replacing their original scene encoders with the powerful DynoV2 encoder. They measured performance using AUC, which stands for Area Under the Curve, a score where higher is better, and L2 distance, which measures error, so lower is better. What's fascinating is that the original models consistently outperformed the versions with DynoV2 swapped in. This result proves that a powerful encoder isn't a magic bullet. You need a decoder specifically designed to work with it, which justifies Gaze-LLE's new design. And this diagram shows us the architecture of that new Gaze-LLE model. On the left, the model takes the full scene image and feeds it into the frozen DynoV2 backbone. This backbone acts as a powerful scene encoder, breaking the image down into a grid of feature tokens, which are like small packets of information. Then comes the key innovation, head prompting. The model adds a special learned position signal, only to the tokens that represent the person's head. This combined information then flows into the very small, trainable gaze decoder, which produces the final gaze heat map. Okay, so this table really dives into why the Gaze-LLE architecture works so well. The researchers systematically tested three key design choices. First, when to integrate the head position, either early on or late in the process. Second, what kind of decoder to use, a traditional convolutional one or a transformer. And third, whether they needed a separate branch for the head, or if the scene branch alone was enough. The results are super clear. Looking at the AUC score, where higher is better, you can see that late integration and a transformer decoder are the winning combination. But the most striking result is that removing the dedicated head branch, going from H and S to just S, has almost no negative impact. This proves that a separate head encoder is redundant, which is a major simplification over prior work and a key insight of this paper. So after validating those internal design choices, the researchers then tested Gaze-LLE against other leading models. This table shows the results of that cross-dataset evaluation, which is a tough test of how well a model generalizes to new unseen data. And the results are fantastic. Across the VAT, Go-O-Real, and Child Play datasets, both the base and large versions of Gaze-LLE set new state-of-the-art scores. They achieve higher AUC and lower L2 distance, showing that this streamlined approach is not only more efficient, it's also more accurate. Alright, and this next table really quantifies those claims of efficiency and accuracy. Here we see Gaze-LLE compared against a whole suite of previous models on the gaze follow and video attention target benchmarks. The key takeaway is in the learnable params column. While other models have anywhere from 29 million to over 135 million parameters, Gaze-LLE has less than 3 million. It achieves its state-of-the-art scores with an order of magnitude fewer parameters, and it does so using only the raw image, unlike many competitors that require extra depth or pose data. To wrap things up, the Gaze-LLE paper is a fantastic example of how simplifying a model can lead to huge gains. The key insight was that a separate head encoder just isn't necessary. By removing it, the researchers created a model that's an order of magnitude smaller and faster, yet more accurate and robust than previous methods. This work really pushes gaze estimation forward for real-world applications. Thanks for tuning into the AI Research Roundup. I'm your host, Alex.